I'm aware this is the last talk of the symposium, so I'll try to make it a little bit lighter, and also it's designed in such a way that if you kind of zoom out for some time, then you can maybe hopefully kind of start thinking about it again a little later on, because it has a few relatively disjoint parts. So categorical probability itself is a pretty old subject, I guess, going back to the 1960s, more or less, with work of Clavier in particular, and also some people in information geometry have considered categorical approaches. But what I'd like to talk about here is something much more recent, and this particular approach to categorical probability based on Markov categories. And this particular approach seems to be quite successful in the sense of reproducing substantial amounts of categorical probability and statistics within a purely categorical framework. And so as I was preparing the talk, I was kind of deciding on what exactly to talk about, which kind of results and what sort of developments to talk about. And I decided that it would be most fun for the audience here if I just focus on the results of my companions and the work and results of my companions. So here they are. As you can see, they're all pretty junior. So at a level from kind of early master student to early postdoc. And so yeah, this is also supposed to indicate that in categorical probability, there's still a lot to do for junior people. And so also supposed to be, in some sense, an invitation for anyone who's interested to maybe think about this. And I'll also propose some further, propose some further avenues later on. And yeah, I would be happy to talk about things. All right, so, but before getting into the details, maybe I should just, some of you may also have seen versions of this slide already, talk about, briefly mention relevant references. So I guess the main two references that have introduced the subject are the first two, a paper by Cho and Jacobs in, well, computer scientists who come more like from probabilistic programming, I guess, who have considered these Markov categories. And then a paper that I wrote a little later. And since then, there's been quite a few papers going into more details and actually developing probability theory and statistics more within this framework. And particularly worth noting is maybe also Arthur Parsingat's work, because he has versions of these Markov category stuff for quantum probability. So I'll focus on the classical case only, just ordinary probability theory, while Arthur also works on, just to indicate that there is work also touching upon the quantum case, which some of you may be interested in. We've also held an online workshop last year, Categorical Probability and Statistics, where many of the talks were also presenting other approaches. So I can't claim that this particular one of Markov categories is somehow universal or unique or something, and there's more in the videos that are available on YouTube there. All right, so, but again, before I get to the definition, I should maybe again say a little bit about the big picture. So there's traditional probability theory. It's kind of says what probabilities are. It says what probability measures are, defines these things in terms of measurable spaces, and then real number valued probabilities. And so in this sense, it's kind of analytic, like analytic geometry is analytic, where you have coordinates in the plane. But categorical probability, in contrast, is more synthetic in the sense that it doesn't define these concepts in terms of more primitive ones, but it axiomatizes these concepts in some sense. It doesn't say what probabilities are, it says how probabilities behave by giving axioms for those. And yeah, I mean, this kind of situation, of course, we know also from other contexts, like concrete number systems versus abstract algebra are kind of like this. And more recently, maybe also, the contrast between traditional homotopy theory and homotopy type theory comes with the same dichotomy between analytic and synthetic. Concrete models on the left, and then a more like axiom and induction system on the right. And in particular, in what I'm going to talk about, categorical probability, there will be no numerical probabilities. So it's more abstract than that. All right, so there's a lot of reasons for why one might want to do this. And maybe I'll just try to go briefly through this, not spend a lot of time on it. So there's certainly, I guess most of the people who have studied categorical probability in the past few decades have done it from a computer science perspective, probabilistic programming in mind. Nowadays, of course, there's also people who think about it with a bit of machine learning perspective. There seems to be some interest there for machine learning people. We can hope to prove theorems in greater generality because it's based on, well, on axiomatics that may have other models too than just usual probability theory. And we typically also seem to get more intuitive proofs of theorems. Yeah, and ultimately we can hope to prove also then theorems of higher complexity because the proofs are more intuitive. We don't need to go all the way down to the details of the measure theory and all that. And a related advantage that maybe we can ultimately do simpler teaching of probability theory. And hopefully my talk will be achieving a little bit of teaching of probability theory as well. Yeah, so these are the kinds of reasons we might want to do this. And so now here's the definition, the categorical definition of what type of category theory this is. So yeah, a Markov category is a symmetric monodal category which has extra structure. So maybe some of you will know about hypergraph categories, which are supposed to formalize categories of networks. And Markov categories are pretty similar to that. And that every object is assumed to come with particular structures. So every object X, there's a distinguished morphism from X to X tensor X. My string diagrams go bottom to top. And a distinguished morphism from X to the monodal unit. And you're supposed to interpret these, to think of these as somehow copying and discarding. So copying, just you copy the value of an element of X, and on the right where you just discard it. And then given this interpretation, it's natural to impose these equations down here, which just say that these structures should make every object into a commutative comonoid. And all of these obviously hold in this interpretation and are reasonable. And moreover, we should impose that when we apply a morphism as at a bottom equation, and then we discard its output, that should be the same as discarding its input to start with and not applying the morphism. And there's some more assumptions in this half sentence interacting well with the monodal structure. As one would expect, these structures can't be specified completely independently on all the objects, but there's some sort of coherence condition. Basically that on the tensor product object X tensor Y, these structures should be exactly the one that you get when you take the one on X, you get the one on Y, and then you put them together using the symmetric monodal structure. Okay, and so what is this actually axiomatize, or what is this the theory of? And the idea is that the objects are something like, okay, so one particular model of this, one particular Markov category would be Finstock, and this is in some sense the paradigmatic Markov category that describes probability theory, or at least discrete probability theory. I don't want to go too much into the measure theory today, so I'll just stick to the discrete case. And here the objects are finite sets, X and Y. And the morphisms are stochastic matrices, which we're supposed to think of as somehow functions which contains some randomness. So the output is not uniquely determined by the input, but somehow a random function of the input. And more concretely, such a stochastic matrix is going to have entries f of y given x, where x indexes the columns and y indexes the rows. And what this means is the probability, what this particular entry or value means, which is a real number, is the probability to get an output y given an input x, or when you feed an input x to the morphism. And well, then this is supposed to be conditions that amount to saying that for every x, these probabilities should assemble into a probability measure on the codomain set. So then composition is given by what's called a Chapman-Kolmogorov formula, but that's just a fancy name for matrix multiplication. So if you look at what happens here on the right-hand side, it's just ordinary matrix multiplication of these stochastic matrices. And it's also quite easy to see that then these conditions are preserved and they hold for the composite morphism. So a morphism from the monodal unit, so one element set, to any x is, well, that's the probability distribution on x. In this case, we have no input, so it's just a bunch of probabilities on x. So a general morphism, well, yeah, as I said, is a function with some randomness intrinsic to it and comes under, I mean, you may have heard of it as under many different kind of names. Markov kernel, some people call it probabilistic mapping. In information theory, it's also called a communication channel. It's exactly the same thing. And well, yeah, so the monodal structure is defined to be just a Cartesian product at a level of objects. And at a level of morphisms, it's given by just ordinary multiplication of the corresponding, so entry-wise, or in other words, the Kronecker product of matrices. And this implements stochastic independence. So independence and probability and statistics means multiplying probabilities. And this is exactly what this does. So when two morphisms are composed in parallel like this, we're just considering them as somehow operating stochastically independently. And well, the copy maps are sort of the obvious thing. They just copy the input. And so they're going to output the input little x with probability 1 and probability 0 otherwise for any other kinds of outputs. So this way we get a Markov category. But this is only one out of many. So for example, something else that we could do, we haven't actually used any properties of the real numbers in this construction. I mean, by none, I mean really none at all, other than that we can add and multiply real numbers, and that this additional multiplication satisfies the usual equations. And so this means we can do the same construction with the real numbers replaced by any semi-ring R. So meaning that we just need to have, well, additional multiplication in such a way that this forms, yeah, one distributes over the other, and that they form just usual commutative monoids as usual. Oh, I forgot to say, this should be saying commutative semi-ring R. Another example, besides the non-negative reals, would be the Boolean semi-ring, which is just a semi-ring consisting of 0 and 1 with all the usual arithmetical rules, apart from 1 plus 1 should be equal to 1 again. In this case, when we do this construction, we get a classic category of the non-empty finite power set monad on fin set. And so this is a Markov category that describes non-determinism in the computer science sense. It's basically like REL category with finite sets and relations, apart from that for every input, every element of the input set must be related to at least one element in the output set. Then for measure theoretic probability, which actually is sort of the main intended semantics that we actually want to be working with, we can look at things like classic category of the jury monad. But yeah, don't want to talk about measure theory today because I don't want to assume that people know measure theory. So then, but these axioms mean more operationally is I think one can say that they axiomatize somehow a theory of information flow, right? And if you draw string diagrams now for Markov categories, they model something like the flow of information, where information sort of propagates through various information processing units, and information can get copied and it can get destroyed. And that's exactly it. So that's exactly the structure that we have in order to talk about this sort of thing. So for example, we could talk about a medical trial where the outcome of the trial for any given patient was going to be probabilistic, of course. So it's not going to be uniquely determined by anything. Certainly the thing that it ultimately depends on is the patient condition. So this is sort of now morphism without any input. And then it also depends on what exactly you treat them with, and it depends on how well they comply with that intended treatment. And now here the point is that both the compliance, the level of compliance, and what treatment you do on them, well, that will depend on the patient condition. A sick patient is more likely to comply with the treatment. And so that's why we need this copy here. We sort of need to copy the information about the patient condition because it influences both the compliance and the treatment. And well, the treatment actually in two ways, both directly and indirectly. And so this sort of stuff we can, is what Markov categories are sort of designed for. And this is closely related to causal networks, and another kind of precursor to Markov categories being Brendan Fong's 2012 master thesis, where he hadn't kind of made this explicit, but Markov categories are pretty much there. All right, so now determinism is, well, I was saying a general morphism is a function with kind of randomness. That's how we can think about a general morphism. But then, so how do we distinguish those morphisms that do not contain any actual randomness? And now there's a categorical definition for these. And this is what's written down here, definition of deterministic morphism. And well, yeah, I can't really claim this to be new to Markov categories because this goes, again, as kind of history and various versions. And so the idea is that if a function, so now imagine this function f were to contain some randomness, that at least for some values of the input, it would do something actually random. Well, in that case, if you feed it that input as on the left, then in some cases, the two outputs will have different values. But if you look at the thing on the right, here, it's the outputs of one application of f that are copied. So in this case, the two outputs will always be exactly the same. And so that means if f has some genuine randomness in it, then this equation will not hold. And likewise, conversely, if f does not do anything actually random, then you can basically use the same way of thinking to realize, yeah, then this f will satisfy this equation. So this sort of motivates this categorical definition, but of course, it's just an interpretation of it. I mean, this is the definition itself in this axiomatic synthetic framework of determinism. Okay. So, and then one can prove purely string diagrammatically that these deterministic morphisms form a monodal subcategory, first of all, but actually a Cartesian monodal subcategory. So that the monodal structure on this subcategory is actually the Cartesian product. So you can prove that it implements products. And in my example of Finstock as the Markov category, this subcategory is on precisely Fin's set, which should then make sense because, well, those stochastic matrices that do not actually do anything random are only those that are, where all entries are 0 or 1. And then because of the normalization conditions here that I had in these equations, these conditions, it follows that those correspond exactly to the honest functions. All right, so now let me get to the first result of what I had sort of the main part that I had wanted to talk about. the work of my companions. So one of these is, and this is sort of, okay, let me kind of say before this that we've proven by a number of classical results in probability theory and statistics based on these axioms and a bunch of additional conditions on particular that impose further conditions on Markov categories. And one of these results is the so-called 0-1 law of Hewitt and Savage. And so here's the classical formulation that they gave in one version of it. And it says that if you have an infinite sequence, or yes, say countable sequence of independent and identically distributed random variables, and S is any event depending only on these, and is invariant under finite permutations, well then the probability of this event is either 0 or 1. But the theorem itself does not tell us which. And this is kind of the crazy thing about it. You can prove very generally that a certain type of event will have probability 0 or 1, but it doesn't help you to decide which one it is, and that's typically actually the more difficult thing to do when you apply this. And yeah, if you don't know about random variables and what these phrases mean, I hope that's fine, because now in the next slide, so here's the categorical formulation, and I sort of hope that this will be a little more intuitive. And so this, for now, involves a bunch of things which I haven't defined yet, but at an informal level, I hope that there will be, that it will make some sense. So what it says is that if you have some state like this, or we can say a probability distribution in a certain suitable kind of Markov category, and we have another morphism S, which has infinitely many inputs. So this is basically going to be a morphism from a sort of tensor power x to the countably fold tensor. And we have a certain definition of what this sort of thing is, which I can get to if anyone wants to see the details. But for now, let me just pretend that this sort of thing makes sense. And then it just produces some output and some other object t. And if these are such that S is deterministic and permutation invariant, meaning concerning permutations on its inputs, then we can conclude that also the composite morphism drawn at the bottom there is deterministic. And so this corresponds, or actually generalizes, this classical statement in that we have these infinitely many independent and identically distributed random variables. That corresponds to the fact that down here, I plug in these infinitely many copies of P. And these are all independent because, I mean, these are all just tensor products or the monoidal products of the original P. Infinitely many of those. And as I was saying earlier, the monoidal structure implements stochastic independence. And yeah, depending only on the xn, this corresponds to S being deterministic. And then, well, the permutation invariance, that's exactly the same. And so the conclusion that this morphism is deterministic then also corresponds pretty much to a generalized version of this. So here, deterministic in this classical case just means, well, taking probability 0 or 1. And this way we can even understand maybe a little better why this statement is so weird. Why does it give us only probability 0, 1, but doesn't help us deciding which? Well, that's because here in the categorical statement, what we really get is a statement about a particular morphism being deterministic. And that, at least to my mind, that makes good sense. Yeah, by the way, if there's any questions or anything, please feel free to interrupt. I'm happy to try and address them, so as not to hold just a monologue.
Okay,
Yeah.
I just posted one in the chat. In the previous slide, do you need them to be indexed by the natural numbers, or can you just state this more generally?
Yeah, great question. So we actually have the statement not just for natural numbers, but for any infinite cardinality. So they need to be indexed by some set which is infinite, but then it works for any infinite set, as long as the relevant infinite tensor product exists.
Great,
Yeah,
thanks.
thanks.
I had a
Okay, and so
question.
now, yeah, is there?
Yeah. How would you draw the string diagram saying that S is deterministic?
Oh, right. Yes. So, well, we're sort of cheating a little, and we've introduced a new notation for objects which are these infinite powers by drawing them as double wires. Oops, sorry, this was not quite intended. Drawing them as double wires. So in this kind of cheating notation, I would just use the usual, basically the usual definition. Oh, and now I realized I can't write further to the right anymore, so sorry, I'll have to move this. Okay, so I guess this is not part of what I'm about to write now. And yeah, so now just applying S and copying the output, but this is the cheating definition, and I guess this is not what you had wanted to see. But part of the definition, huh?
No, you can
Part of the
continue.
definition of Kolmogorov power is that it also determines what the co-multiplication or the co-monoid structure on such an infinite tensor product actually is. And so I think there isn't a good way to draw this in terms of string diagrams, other than to kind of say that when we have these infinitely many wires, then we just kind of draw them like this. And so I could also draw the left-hand side. Again, I'm running at a boundary here. Could draw the left-hand side of this equation like this. And so now again, there would be the dots here indicate these are infinitely many objects. And basically the condition that we have for the Kolmogorov power, which determines this comonoid structure in terms of that of the factors, is basically such that it identifies this with this thing. So this is how I would draw it either way, like this. Okay, so now the statement of the theorem, as an assumption, I had this adjective causal Markov category here. And so here's the definition of that. It is a sort of causality condition in the sense of the future cannot influence the past. And so a Markov category is called causal if whenever you have an equation which is of the type is on the left, then we can conclude, automatically conclude the stronger equation that's drawn here on the right. And it's stronger because if I now were to discard this third output, well, then I could use the comonoid axioms in order to just eliminate this co-multiplication or this copy map entirely and get the thing on the left, just the co-unitality. But yeah, this axiom is saying that the implication actually holds this way, and we automatically got the stronger equation. And the way to think about it is, one way to think about it is to note that on the left, the two expressions are the same, except in that they differ here sort of in the future of G. And then this difference, which morphism we choose in the future of G, if this does not make any difference, then it can also not make any difference concerning what happened in the past of G. So what we're doing here is sort of looking at the past of G and considering this past, the input of G, that value, also making it into an output and kind of observing it as an output. And so this is how the axiom is saying that it doesn't matter what happened in the past of G if the choice between H1 and H2 does not influence the future of G. And given this, that this sounds hopefully quite natural of a condition, and given that I had mentioned that Markov categories are about information flow, it may be somehow surprising that not every Markov category is causal. And it actually did not seem trivial to find examples of this at the beginning of all of this. But many of them are, and let's say all the usual ones, the ones that I've mentioned, at least the very concrete ones, these are causal and satisfy this condition. Whoops, sorry, now I again pressed the wrong button. Okay. There's another natural axiom for Markov categories that has turned out to be of some use. And instead of related to causality, it's related to the non-negativity of probabilities. And so in a way, it seems to be a categorical way to talk about the non-negativity of probability. And what it says is that if a composite morphism GF is deterministic, well then, again, we can conclude an additional equation, which is a priori not obvious, and namely this one. And the intuition for this is that if a deterministic process, so which in this case would be sort of this composite one, if this has an intermediate result, namely this one, the output of F that becomes the input to G, and when we're now observing this intermediate result, then given that the overall process is deterministic, we might as well compute that intermediate result separately by an independent application of the first part of the process. So this is what the axiom, how one can think about this equation. And again, not every Markov category is positive. And so kind of a very recent result that we have, and which is now the second thing proved by one of my companions, is the relation between these conditions. Oh no, sorry, I actually wanted to talk about something else before that. So yeah, which is again another result by my companions. So namely, which Markov categories are positive? And so Markov categories are very often Kleisli categories of monads. Like Finstock is very similar to the Kleisli category of the distribution monad. And then this category for non-determinism that I had mentioned is the Kleisli category of the non-antifinite power set monad. And so very generally, whenever you have an affine commutative monad on a category with finite products, then its Kleisli category is going to be a Markov category. And so now here's a very recent result on when this construction results in a positive Markov category. And yeah, this result says that this happens whenever the monad T is strongly affine. And this strong affineness is a condition that was already had been introduced in categorical probability by Bart Jacobs a couple of years ago. And it's saying that a certain square is a pullback. I can also explain in more detail what this means if anyone is interested how to think about it. But yeah, so the theorem is a characterization now when a Kleisli category is positive as a Markov category in terms of the monad, and the realization that this corresponds to a natural and known condition, which was quite surprising to me. And what's also been almost shocking to me is the relation between the causality and the positivity axioms. So they look very different. At least to my mind, they used to look very different. And so, but still one can ask, does one imply the other? What is the relation between them? And what is not so difficult to see is that there are Markov categories that satisfy the positivity axiom, but not the causality axiom. And so we know that one implication does not hold, but now the shocking thing is the other implication is true. The causality axiom implies the positivity axiom. And there's a purely string diagrammatic proof of this, which I'm now going to show, but it's not easy to find, and I had not managed to find it. So yeah, we're basically assuming now again the sort of things that we have in the positivity axiom, a composite morphism GF that is deterministic, and well, the two morphisms G and F that it's made of. And given that, you can prove that this equation holds basically by just, well, simplifying both sides, because we're just discarding things here, so we can apply the co-unitality very easily. And then just use the assumption that GF is deterministic to prove that this equation is true. And so now the point of drawing a complicated equation like this is to apply the causality axiom, because it has exactly the right form for the causality axiom, namely where, so the causality axiom required these sort of composite morphism down here, which is the same on both sides, and then two different morphisms on these kind of legs or arms. And that's exactly the form that we have here. So there's a composite morphism down here. And two different things on top, on the left part, on the left half. But otherwise the same. So yeah, these are equal, so we can apply the causality axiom, and we got this even more complicated equation. And now there's a bunch of similar simplification to this, which now, if you apply these, it turns out that this is exactly the desired equation from the positivity condition here, namely this one. So yeah, it's really not so difficult once you know how to draw these really complicated diagrams, but finding these has been the difficult part. Yeah, all right, and yeah, I'm kind of moving on to the next kind of subtopic, and also the last subtopic already, which is semi-cartesian categorical probabilities. So far I've been talking about Markov categories, a little bit of what we've done with them, and their axiomatics. But it turns out that one can actually do quite a lot of categorical probability, even with a weaker structure in this, even without the copying. I mean, in the things that I've presented, these co-multiplications or the copy maps really have played a very central role, right? It was all about these in some sense. But again, this has been quite surprising to me. There's a lot that one can do without these, and purely talking about discarding only. Symmetric monodal category, which has a natural discarding operation for every object. And this is exactly what's called a semi-Cartesian symmetric monodal category. It's semi-Cartesian in the sense that it has product projections. So those derive because those correspond to discarding parts of a product, but it does not have, well, the monodal structure is not the Cartesian one, so it does not have diagonals, it does not have even non-natural copy maps anymore. An equivalent and simpler way to state this is to set up, and this has been quite well known, a symmetric monodal category C is semi-Cartesian if the monodal unit is terminal. And obviously, when this is the case, then you get discarding maps like this, or projection maps like this, by just applying the terminality, the unique morphism to the terminal object on one of the two factors. And yeah, so we still have the discarding maps and also their naturality equation. So now something that we can still talk about, and something that then plays a central role in the semi-Cartesian categorical probability, are dilations. So a dilation of a morphism F, not a Markov category anymore, right? But just a semi-Cartesian symmetric monodic category. That of F is any G which has an additional output, such that when you discard that output, well, then you recover F. And what this somehow describes intuitively is that G is a particular implementation of F, which can sort of leak information to the environment E. That, again, both F and G describe a kind of information flow, but G, and also the same sort of information flow or computation, but G keeps track of what happens concerning information leaking to the environment, while F does not. It seems that these dilations then form some kind of two-categorical refinement of C, but this is something that we haven't worked out yet in full detail, but there seems to be quite an interesting two-categorical structure also here waiting to be explored. So now here's a kind of surprising definition. And to indicate how much one can still do with this purely semi-Cartesian concept, and namely that we call a morphism F non-creative if any dilation of F has this particular form that's drawn here as a string diagram. Namely, it's given by a dilation H, which is a dilation of the identity. So meaning that satisfies this equation. And then we just apply F to the original sort of copy. And yeah, then, so this is a definition that one can kind of come up with. And the way to think about this is, again, that what this captures is a sense in which F is deterministic. So while I had earlier presented a definition of deterministic morphism in a Markov category, this is a definition, a related definition that applies in any semi-Cartesian symmetric monodic category only. And now one can prove that in a positive Markov category, well, then one can actually still apply this definition of non-creative morphism and kind of wonder what are the non-creative morphisms. And turns out that they're exactly the deterministic ones. So although the definition of determinism involves the copy maps, we can, if the positivity axiom at least holds, we can characterize them in a way that does not even involve the copy or the co-multiplication anymore. And this is quite nice. And again, I think there may be a lot more that one can do with this. So yeah, and going actually further, we also have now characterized positive Markov categories as semi-Cartesian categories with extra properties. So this means, in particular, in a positive Markov category, all the comonad structures on the objects are uniquely determined. There is no choice anymore. It's like in a Cartesian monodal category, every object also is a comonoid in a unique way. But this is actually true more generally for positive Markov categories. And that's why when it is possible to characterize them as particular semi-Cartesian symmetric monodic categories only. Okay, so this was a kind of tour of the things of some of the things at least that my companions have done. And yeah, I think there's a lot more stuff to do. I mean, we're still kind of very much at the beginning.
Can I ask a question about the previous slide?
Yes, please.
So you said that positive Markov categories are semi-Cartesian. So is a generic Markov category not semi-Cartesian? Because the final axiom looks like it forces semi-Cartesianness, but it wasn't entirely clear.
Yes, you're absolutely right. And sorry if this was a little confusing, and so thanks for asking. Every Markov category is semi-Cartesian, because that's just the axiom, basically the axiom here. then the naturality of discarding implies that.
Yeah, okay.
Together with, actually it's a little subtle, it's this, together with the assumption that a discarding morphism of the monodal unit I is the identity on I. But these two things together imply the semi-cartesianness. Whoops, now I'm kind of going the wrong way, and okay.
Sorry for disrupting, but yeah, okay, thanks.
And but this equivalence and these statements that I've made here only apply for positive Markov categories. Right. And in a general case, I mean, if it's not the comonad structures on a general semi-Cartesian or even on a Markov category, is the co-multiplications are generally not unique. So we cannot hope for a statement like this without the positivity condition. Yeah, so there's a lot of things somehow that feel like they could be done and should be done. And in particular, we've worked a little bit on the law of large numbers and have some maybe tentative results in that direction. I mean, that is in some sense, I would argue at least that the most fundamental and important result of probability theory. And so if this theory is supposed to be a serious contender for a new foundation for probability theory, which is something that I'd like to be able to claim, then we should better have a way to treat the law of large numbers as well. And this is something that's current work in progress. But there's many other things to do, and we certainly, I think, don't have the time to do all of these and the mental capacity to do all of them. So if anyone is interested in just doing this, doing anything in categorical probability, I'd be happy to help and try and provide, share my experience, or just yeah, help in any way I can. So something that is, I think, could be quite interesting to do would be to develop some kind of theory, or to develop the usual theory of graphical models in more detail within the categorical framework. So in particular, things like Bayesian networks that describe causal structure, and really the theory of causal inference. There's all these algorithms and criteria for what we can say about which things influence which other ones, which are for distinguishing cause and effect, and it really feels like that those algorithms and results really should be part of a categorical framework. Yeah, there's more stuff like going in the direction of really classical and probability theory and difficult measure theoretic results. And one particular one that I think is kind of within reach now is this so-called Aldous-Hoover theorem, characterizing basically random graphs. Maybe some of you have heard of this concept of a graphon, which is some kind of infinite random graphs with a lot of symmetry. And this kind of result, I think, is within reach of the methods that we have now. Yeah, it would be nice to be able to do information theory as in kind of Shannon's theory of communication, at least the sort of start of that, and develop some of the basics. A big thing is that many people also have asked about is that one should generalize to enriched categories, because so far what we can talk about are mostly qualitative results, as in either two morphisms are equal or they're not equal. But really a lot of probability theory is more quantitative, right? It's about inequalities. And so one can hope to now redo all of this using things like categories enriched in metric spaces. So we can compare two parallel morphisms and how similar, how close are they, and thereby talk about quantitative things. And yeah, again, we have some ideas of what to do along these lines, but it's also pretty much open. There's also a big landscape of Markov categories. I mean, what we've done so far is mostly to look at the usual probability so the intended semantics, so to speak, in Finstock, or well, more generally then in measure-theoretic probability. But there's a lot more stuff to be looked at, and I think it'd be interesting to just instantiate some of the existing results in other categories and see what they amount to. And also, I have the feeling that a lot of what we've done, so I briefly applies actually more in a similar way to hypergraph categories. So I had mentioned hypergraph categories as a framework for categorical network theory, whereas a lot of people in applied category theory are using this now. And my feeling is that some of the things actually have analogs for hypergraph categories, in particular things like the causality and the positivity axiom. One can try to write these down in a more in a way that applies in hypergraph categories. And I did actually at some point ask Brandon Fong about this, whether they would hold in that case for electrical networks, for example. And he seemed to be optimistic that, for example, the positivity axiom would hold. And it seems reasonable. It could be of some use for also to develop network theory in hypergraph categories further. Okay, yeah, this is what I wanted to say. And so thanks a lot for listening. And I hope it's been a little bit interesting.
Very interesting, thank you. Let's all thank Tobias. You're free to unmute yourselves if you like.